Okay, let's continue the discussion of a Taylor series. Remember, the Taylor series is the following thing. So last time we had the definition. So you have analytic function. F is analytic. At z equal to z0. Then we know that f is infinitely differentiable. It has all the orders of higher orders derivative. Then we define the series. The series is f of z0, f prime of z0. Let's put 1 factorial here. 1 factorial is still 1. F double prime of z0 over 2 factorial z minus z0 squared. And the general term will be the nth derivative of f evaluated at z0 divided by n factorial and times z minus z0 to nth power, and continue this to infinity. And this is called the Taylor series. Of f around z0. Okay, so that's the definition we discussed last time. And when the z0 is equal to 0, so when z0 is equal to 0, then you don't have z minus z0 to nth power, you just have z to nth power. In this case, the series is also called the Maclaurin series. For f. Okay, so we introduced or we mentioned these two definitions last time. These definitions are from the polynomials, and you see that when you have polynomial, you have some similar construction, but not like unlike the polynomial. At this moment, we only say this is a Taylor series associated to the function f. We don't mention they equal to each other or not. So the theorem 3 says sometimes they equal to each other, sometimes they don't. So if f is analytic in the disk is a z minus z0 less than some big R, capital R, fixed, then the Taylor series here, let's put this symbol 2, the Taylor series 2. The Taylor series 2 means this series converges to f of z for all z in this disk. Okay, so the statement of the theorem just guarantees that inside the disk, the function f is equal to the limit of the Taylor series. Okay. Furthermore, this is the open disk. Furthermore, the convergence of the series is uniform in any closed subdisk z minus z0 less than or equal to r prime, and r prime is less than r. So in any closed subdisk, so you have this open disk, center is z0, and you have the radius r. And in this open disk, we only know it converges, the series converges. But whenever you get a subdisk, it's closed. Whenever you have a closed subdisk, then it becomes uniform. The convergence is uniform. Okay, so that's what the theorem 3 says. We can only claim the equivalence convergence inside the disk. So there's certain conditions about the equality between the analytic function and its corresponding Taylor series. Okay. Now let's see how do we prove it. How do we prove it? Okay. So the proof also depends on the Cauchy integral formula. So proof. We are going to prove, we will prove that for any small or subdisk, for any closed subdisk, for any closed subdisk z minus z0 less than or equal to r prime, the series converges to F uniformly. The series converges to F uniformly. We only prove this. We claim this is sufficient. This is sufficient. Why? Because for any point z inside the open disk centered at z0 with radius r, okay, so it's inside the open disk, then the distance, then there is an r prime with the distance between z and z0 less than or equal to r prime and less than r. Okay? So whenever you have a point inside the open disk, it's never on the boundary. If it's not on the boundary, there's a certain distance. Then you insert r prime there. So this point z is included in this uniform convergence case. So it means the series, then the uniform convergence on the closed disk, closed subdisk, let's put z prime here, implies convergence at z prime. Okay, so that's a reason we only show the uniform convergence for every subdisk centered at this z0. Okay. Okay, now let's redraw this circle. So we have a open circle and we have a closed circle. We have a closed circle. Remember this, we are going to study every point on this closed circle, including the boundary. So when you try to apply the Cauchy integral formula, you cannot use a boundary, because if you use that boundary, if you use this boundary, then the function is not well defined on the boundary. Okay, so we are going to apply, remember that f of z is 1 over 2 pi I integral c f of theta minus zd theta. So this c in this case cannot be the boundary of this closed disk, because if the boundary is a closed disk, z has a problem about this denominator. Okay, so we will have problem. So this we need, or we will use the Cauchy's integral formula. So C cannot be the boundary of this closed disk. You just cannot do it. If you do it, this denominator will be 0 when z is from the boundary. Since you cannot use the boundary of this closed disk, let's draw a slightly bigger disk, a slightly bigger circle to surround this closed disk. Any circle will be okay, but here let's just get a nice quantity. So we choose r plus r prime over 2 as the radius. Okay, so we get the circle exactly between those two circles. Okay, so this is r plus r prime over 2. The radius is this. Let C be the circle z minus z0 equal to this r plus r prime over 2. Okay, it is still inside the domain and it contains this closed disk totally inside. And of course we choose counterclockwise orientation, or here we just say positive orientation or the direction. Okay, right? So it's this way. So C is going to be this curve. Okay, now assume we have this. We have the integral formula. Now let's check. In the integral formula, basically we are trying to study this function 1 over theta minus z. 1 over theta minus z, let's see the trick. Okay, so we subtract z0 for theta and z, and we factor out theta minus z0. Okay, just factor out. So group them. Okay. Check here. This z is from this closed disk, and theta is from this middle circle. So we know that the distance between z and z0 is strictly less than the distance between theta and z0. So this is a complex number with modulus less than 1. Okay, so keep this in mind. When you have this 1 over 1 minus r. So this is 1 over 1 minus r. R has a modulus upper value less than 1. What do? We have the following thing. We minus 1 minus r to n plus 1 plus r n plus 1 over r. Okay, so that's the trick or the computation in the textbook. And this one we can factor out the numerator and cancel 1 minus r. So you get r squared plus r to n, and this part you get r to n plus 1 over 1 minus r. My bad, 1 minus r. R to n plus 1 over 1 minus r here. Okay, it's like the remainder. Okay, so we apply this to our computation. We get 1 over theta minus z0, and then we have 1 plus this term. So you get z minus z0 over theta minus z0 up to z minus z0 over theta minus z0 to the nth power, see here, to the nth power, and plus the numerator, z minus z0 over theta minus z0 to the power n plus 1 over 1 minus this complex number. Okay, so this is this part is the argument why you can get this in the textbook, right? Okay, so we only have finitely many terms. So far, we only have finitely many terms. It's like this part is more or less like the partial sum. Here is the remainder, right? So we take the integral. Remember that we have this. We take the integral. So the integral of times f of theta and take the integral. We will get f of z. Let's put it here. F of z is equal to 1 over 2 pi I, the integral f of theta over theta minus z0 d theta. So this term comes from this first term times 1, so you get this. And second one, 1 over 2 pi I integral along C, f of theta, so this term, you will have z minus z0 theta minus z0 squared d theta. And when you get the nth term, it's 1 over 2 pi I, the integral along C, f of theta z minus z0 to the power, to nth power, theta minus z0 to the power of n plus 1. Check here, you have nth power. Here you have theta minus z0, so that's why you have n plus 1 d theta. And plus this remainder, plus 1 over 2 pi I, the integral along C, f of theta, and it's very complex. Let me just finish the writing. It's not z minus z0, theta minus z0 to the power n plus 1, and this and then this term times this term. You see here, this term times this term is just a theta minus z. Theta minus z. And d theta. Okay. So it's just a multiplication with f theta and do the integral. And plus the Riemann integral formula. Okay. So let's check them one by one. So the first term, we know that the function f is analytic over the over this open disk. So this, by the Cauchy integral formula, it is equal to fz0. Okay, it's exactly fz0, and this kind of term, let's check the general term. Okay, so first of all, z minus z0 to nth power is a constant. You can move it forward. And then you have the integral check what this is. This is exactly the nth derivative but divided by the factorial. So this is equal to the nth derivative. Be careful about the shift of the index, and divided by n factorial. Okay, so we do have that higher order derivative formula here. Okay, so just this part. If you don't remember it, you can go back and check it. So what we have the first n plus 1 terms. Now we have f of z is equal to the first term is f of z0. f of z0, this does not have derivative. The nth term, you see the nth term, it is the nth derivative evaluated at z0 over n factorial n times z minus z0 to nth power. And then plus the tail. This tail is here. It's very long. The tail is here. This tail, let's call it t sub n, tail. T sub n of z. T sub n of z. Okay, so let's put it here. Let's define it. So in order to show the uniform convergence, it suffices to show that t of z0, tn of z converges uniformly to 0 on this closed disk. So if we can show that this tail converges to 0 uniformly, then we prove that the Taylor series converges uniformly to f of z. Okay, so we're going to study this term. Okay, now let's see what this is. We have Tn of z. Let's copy it again. It's 1 over 2 pi I integral along c f theta over theta minus z, and then times z minus z0 over theta minus z0 to power n plus 1 d theta. Okay, so this is the function. In this function, let's see what we have. We need to borrow the graph here. We borrow the graph here. Z is here. This is z. At most here. And theta is here. Let's not put z here. Z is possibly here, this way. Z is possibly here, theta is here. Okay, so the distance between theta and z, let's see the denominator. The distance between theta and z, it can be very far as you see, this distance plus this radius plus that radius. So it is bounded bounded by, it's less than or equal to r prime plus r prime over 2. One radius plus the other radius. And theta minus z, the distance is greater than what? Greater than the difference of the distance. The difference of the distance is like this. Okay, so from the geometry, the plane geometry, from here, from this graph, you observe it, you will see that this theta minus z is between r minus r prime over 2 and r plus, you see here it becomes 3r prime over 2. This is a complete description. So far we don't know which part we need, but we do find this boundary. And z, again, z minus z0 is less than r prime, less than or equal to r prime, z minus z0. And the theta minus z0 is equal to r plus r prime over 2. It's on the intermediate circle, so the radius is a fixed number. Okay, and the length of C is 2 pi r, 2 pi the radius. Two pi the radius. Okay, so with all these quantities in mind, then let's estimate the absolute value of t sub n of z. It's less than or equal to 1 over 2 pi integral along c f theta, absolute value, theta minus z, z minus z0, to power n plus 1, and theta minus z0 to power n plus 1, and d theta. Okay, so that's the basic estimation. And now let's do it step by step and find the stuff. That's all equal to 1 over 2 pi. And f theta, it's a fixed circle. Remember this, so far we have a fixed intermediate circle. So f is analytic, so f is continuous. Absolute value of f theta is continuous. So it has a maximum value of f theta. Theta belongs to C. So this is a fixed number. It is determined by r and r prime, but once you fix r and r prime, this is determined. And this part, we need less than inequality. When we have less than inequality, we need this part. You see? If you have it greater than or equal to greater than r minus r prime over 2, when you flip it, you get less than, so times the reciprocal. So it's times 2 over r minus r prime. Okay, so that's this theta minus z. And z minus z0 is less than r prime. So you have r prime to nth power. R prime to nth power, n plus 1 power, n plus 1. Theta minus z0 is this term. So over r plus r prime over 2 to power n plus 1. Okay, and what else? And this the length of the circle. The length of the circle is pi r plus r prime, r plus r prime. Okay, and let's simplify it. So you have a pi, you cancel with a pi. Have r, you cancel with this r. So we have the maximum value theta belong to C, f of theta. It's a fixed. It does not depend on z. And 2 cancels. So r plus r prime, r minus r prime, r plus r prime, r minus r prime. Okay, this is a fixed number. And then you flip this 2 to the numerator. It's 2r prime over r plus r prime to the power of n plus 1. Okay, in this expression, there's no z. There's no z. Only r, r prime, and n. So first of all, it's uniform. And 2r prime over r plus r prime is less than 1. So the nth power will approach 0. So we do prove it converges to 0, it converges to 0, and the convergence is uniform. The uniform on this closed subdisk. Uniform on the closed subdisk. So we finish the proof. Okay. After this proof, we can see that whenever you have an analytic function, you may find a disk. If it is analytic over the open disk, then inside that open disk, the analytic function is equal to its Taylor series. Is equal. Okay, so for example, it's end of the proof. For example, let's see if we have log z of z0 and log of z, z0 is equal to 1. Log of z, z0 is equal to 1. Okay, so we know that the Taylor series involves a higher derivative. So we just try to observe what is a derivative. So the derivative of log is 1 over z. The second derivative of log is negative 1 over z squared, and so on. After some computation, you can get the pattern. The j's derivative of logarithmic function is equal to negative 1 to power j plus 1, j minus 1 factorial. You can put a j minus 1 also. And z to power negative j. J is equal to 1, 2, and so on. Okay, so that's the higher derivative. All the orders derivative. And then we are going to evaluate all the orders of derivative at z0. z0 is 1. At 1, dj dzj log z at 1 is just negative 1 to j minus 1 over j minus 1 factorial. Sorry, my bad. It's not over. J minus 1 factorial, this is a multiplication from here. Okay, so this is the j's derivative. Then the Taylor series. What's the Taylor series? The Taylor series is going to be, this is the evaluation at 1. Log 1 is 0. Log 1 is 0. Remember, we use this principal branch. We use a principal branch. Number 1 has a argument 0. Number 1 has argument 0, so we have 0. And z minus 1. When j is 1, j is 1, this is exactly 1 over 1 factorial. 1 factorial is equal to 1, so you have 1. And plus this number, when j is equal to 2, j is equal to 2, you get a negative 1 times 1 factorial over 2 factorial and z minus 1 squared. J equal to 3 is negative 1 squared 2 factorial over 3 factorial j minus 1 cubed. 1, yes, cubed. Okay, and so on. So eventually, you will get negative 1 to power n minus 1 factorial, n factorial, and z minus 1 to power n. And if you write a few terms, you will see, first of all, most of the factorial factors are cancelled. So you only have denominator n. It's alternating. So you have z minus 1. This is negative 1 over 2 z minus 1 squared. This is a positive 1 over 3 z minus 1 cubed. And then you will have negative 1 to n minus 1 n z minus 1 to nth power and go. So this is the Taylor series of the natural log, the principal branch. Right? So if you want to write it in the compact form, the sigma notation, it has a sigma notation. You just check it here. It is equal to the sigma. J is from 1 to infinity, no 0. Zero's term is 0. And the negative 1 to j minus 1, and z minus 1 to j's form, and j over j. Okay? You put the j minus 1, j plus 1, it doesn't matter. Okay. And this is valid for what? For z minus 1 less than 1. Why? This is only valid for z minus 1 less than 1. The reason is the following. Remember, we cut the complex plane along the negative x-axis, including 0. So 1 is here. If you want to find an open disk centered at 1 with radius r, the radius 1 is the maximum possibility. The radius 1 is maximum possibility. If you get even bigger, the radius bigger than 1, you will include the part of a negative x-axis. Then function natural log of z is not analytic. So this is the maximum, the largest possible. Even though we know that here function is analytic, here function is analytic, but in our proof we require over the whole open disk function should be analytic. Unfortunately, this part is not. So in other words, you can see that if your point z0 is close, for example, if your point z0 is close to this cutting line, the radius is smaller. If your point is far from this line, the radius is bigger. So the radius in this case also depend on this selection of we call it the center of the Taylor series. Okay, the radius depend on the center in this case. Okay, next. Let's see 1 over 1 minus z around z0 equal to 0. We're talking about the Maclaurin series. Well, let's see the derivative. if you realize this 1 over 1 minus z as 1 minus z to power n minus to power negative 1, you will see that whenever you apply the derivative, you always have a positive sign. There's no negative sign. You have a negative sign here, you have a negative sign here. There's a chain rule. So it is always equal to the j factorial 1 minus z to power negative j and minus 1. This is negative 1 and then minus 1, minus 1, minus 1 all the time. There's no negative sign. Okay? And also remember z0 is 0. So 1 over 1 minus z is going to be equal to, when z0 is 0, you evaluate at 0, you get a 1. And when j is equal to 1, z0 is 0. So the evaluation, let's call it f of z. The j's derivative evaluated at 0 is 1 times j factorial is j factorial. And j factorial, remember that you have to divide it by j factorial is equal to 1. So the coefficient is always 1. So you have z squared, z cubed, and so on. And this convergence disk is at 1 minus z less than 0. Why? It's not 1 minus z less than 0. It's my bad. Sorry. It's a z minus z0. Z minus z0 less than 1. Z minus z0 is less than 1. The reason is the following. This function 1 over 1 minus z is undefined at z equal to 1. Only this point is bad point. Undefined. It's a pole. And your center z here is 0. So the maximum disk centered at z0 you can draw has a radius 1. So z minus z0 can only be at most 1, the ops value, in order to make the function completely analytic inside the disk. Any slightly bigger disk will include this undefined point. Okay? So we always find the bad point and just get the largest disk touching the bad point. The third example is natural exponential function. We know that the natural exponential function for whatever derivative is itself. So let's still choose z0 equal to 0 because it's easy to evaluate. And so you see the nth derivative or j's derivative evaluate at 0 is equal to 1. Check here, e to 0 is equal to 1. So when you divide it by j factorial, you will have 1 over j factorial. So the radius of the Taylor series becomes when z is 0, e to 0 is 1. Then 1. For the first one, it's a z. For the second one, z squared, and over 2 factorial because coefficient is 1 over j factorial, and z cubed over 3 factorial, and so on. And so on. And this function is differentiable everywhere. It's called the entire function. So for any z, e to z is equal to z plus this, because when you get a disk, you can just draw it as large as possible to include this z. Okay? There's no limit. There's no limit. Okay, so we have 3 examples about the equality of the Taylor series. And now let's observe the first and the second examples again, and we try to come up with some conclusion. So the first, log z is z minus 1 minus z minus 1 squared over 2 plus z minus 1 cubed over 3 minus z minus 1 to 4th power over 4 and plus whatever. We have something like this. And for this one, we just do the differentiation term by term. What we have this is 1. This one minus z minus z minus 1 here plus z minus 1 squared and then minus z minus 1 cubed and so on. Right? So it is what? It is the every time you switch the order for the odd part, when you switch z minus 1 to 1 minus z, it is equal to 1 minus z. Here it's for the even part, it doesn't matter what order you put. So by switching the order of z and 1, we absorb this negative sign. We don't want this negative sign. We don't want the alternating series. And then this is equal to the sigma 1 minus z to power n from 0 to infinity. And from 0 to and remember that what is the domain of log z equal to it. So log z equal to it, z minus 1 less than 1. This is a valid domain. Right? Check here, we still have the graph here. Z minus 1 less than 1. Okay, so z minus 1 less than 1. 1 minus z is less than 1. So this one by the geometric series. It starts from 1. So it's a 1 over 1 minus common ratio. 1 over 1 minus common ratio. This is 1 over z. So what do we get? We get the term-by-term differentiation of the natural log function gave you the Taylor series of its derivative. Okay, so this is 1 over z. So 1 over z is a derivative of natural log, and its corresponding terms in the Taylor series are the derivative of each term. Right? So that's an observation. We can do term-by-term differentiation. Okay, so that is the theorem 4. This is just observation. We will claim the theorem 4 and try to prove it. So if f is analytic at z0, the Taylor series for f prime around z0 can be obtained by term-wise differentiation. Term-wise differentiation of the Taylor series for f around z0. And see here you have 2 Taylor series and converges in the same disk as the series for F. This means you see originally you have the convergence disk. Here you have the same convergence disk. That's what it means, the same convergence disk. Okay, let's try to prove it. So the proof is the following. The J's derivative of F prime is the J plus 1's derivative of F, right? So the Taylor series for F prime is given by what? So first you evaluate F prime at z0. This is the evaluation of the original function at z0. And then you continue the differentiation. You differentiate and multiply it by z minus z0. And you get the second derivative. Second derivative becomes the third derivative of the original function. Right? So this is written by the definition of a Taylor series. On the other hand, if we have original Taylor series, we do term by term, term-wise differentiation. Gives us what? Gives us you see this term is 0. This is F prime of z0, and this, because you have the when you do the product rule, you have two cancelled with 2 in the denominator. And the next one, let's write down. And this term give you F third derivative of F at z0, but 3 cancelled. You have 2 factorial z minus z0 squared, and so on. So you compare them. They are term-wise equal, which is the same as above. Okay, the same thing, exactly the same thing. And F is what? F is analytic in the disk. Then F prime is analytic in the same disk. We know that function F has infinite limit derivative, is infinitely differentiable, and all the derivatives are analytic. So they share the same they have the same analyticity over the same disk. So the Taylor series converges to F prime over the same disk as F of z. Okay? F prime of z, F of z. Because they are both analytic over the same disk. So whenever you have the Taylor series, you have the Taylor series will converge based on the theorem we just proved. Okay, so we finished the proof and we stop here and we'll continue next time.